Hey everybody, Zachariah J here again. IVC Pre-Calc final exam. We are coming to the end of the semester. We've all gotten there together. And this is the last exam we have to study for this class. And then we get to start it all over again with Math 3A. Who's excited? Anyway, just a reminder, not the teacher of the class, one of the students in the class, doing this just to help myself retain the knowledge and to help you guys if you're having a little bit of trouble with some of the problems. So I may make some tiny errors or mistakes. Appreciate your comments. If I do, that helps everybody else learn from my mistakes, helps me learn from those mistakes as well. So without further ado, let's get on to question number 1. Use the graph to find the intervals for when it is increasing, decreasing, or constant. So these are our three key terms here. So we'll write those down right over here because they'll be part of our answer. Increasing, we'll want to know when it's decreasing. And when it's constant. So let's look over here at the graph. And since we're doing increasing first, let's just look where this graph increases. And it increases right along this section right here. And that begins at negative pi over 2 right here. And it ends at pi over 2. There's nowhere else that's increasing, so this is all we have for increasing. So we'll just put from negative pi over 2 to pi over 2. That is our increasing portion. Let me grab a different color here and we'll highlight the decreasing areas, and we decrease here and we also decrease here. So we're going from negative pi to negative pi over 2. That's the first one. And then we go from pi over 2 to pi. So back to my green color here. And we'll write that down. So negative pi to negative pi over 2. And this other section, which was pi over 2 to pi. Now that's the whole graph. There's no areas where it just lays flat or stays constant. So we'll just write none here for that guy. For number 2, I've already written the increasing, decreasing, constant section here. But let's look at increasing first again, and we see it's just this portion right here from negative 1 to 1. So I'll just write that down, negative 1 to 1. And then we'll look for the decreasing section. And again, we have two sections for decreasing. This is the first one from negative 3 to negative 2. So I'll write that down so I don't forget. Negative 3 to negative 2. And then we have another section from 2 to 4. So from this 2 right here to this 4. So we'll put that in the decreasing section here as well. So, and 2 to 4. And then this one we actually do have some constant areas. Here's our first constant area, which is from negative 2 to 1. So I'll write that one down. Negative 2 to negative 1. And then we have another one, so I'll just put and here. And that's from the 1 to the 2. So there you go, 1 to 2. Pretty easy so for these next couple, the graph of the function is given. Use the graph to answer the question. Find the number if any at which f has a local maximum. What is the local maxima? So our local maximum on this is at x equals 0. We can see that our highest point is at the 0, and our maxima is the y coordinate, so it is 1. So that's number 3. Done. So number 4, we have a minimum. Whoa, there we go. Because we see a lowest point is down here at -2, but our local minimum is at x equals 0. Again, same as the last problem. X equals 0. And then since this point is 0, 2, it's the y-coordinate is the minima. So the minima is -2. So let's see if we can get this connect. Anyway, pretty easy there. So the next couple, we're going to find a simplified difference quotient for the function. Difference quotient. Well, to remind you what that is, it's f of x minus h, I'm sorry, x plus h, the quantity, minus function x, all over h. And what this means is we are going to substitute x plus h in for the original function where there's an x. So we have 3 over x plus h, and then that is going to be minus the original function, which is 3 over x, and then all of that over h. Now we have this part on the numerator, these two parts, and we're going to have to find some way to get common denominators, but we can do this all in one big step. We can just multiply the top by x plus h times x, and the bottom times x plus h, that quantity, times x. And we can get rid of these fractions on the top and get what we need on the denominator as well. So if we multiply this all out, this first 3, it's missing the x portion, so we can just write that as 3 times the quantity x, because that's what it was missing on that side. X plus h minus 3. Actually, let's write this correctly. I'm trying to do some things in my head and I'm not getting there. So anyway, this 3 was missing the x, and then the other one was minus 3x plus h. And then that's all over h times x plus h times x. There we go. Now we got all that done. Now what we need to do is distribute these 3's on the top. So we have 3x minus 3x minus 3h all over h times. Now I'm not going to distribute this bottom part because I'm going to show you why here in a second, but quantity x plus h times x. Now we have 3 minus 3, so 3x minus 3x. And we can cancel out this h as well. That's why I didn't distribute that on the bottom. Now we have negative 3 over x plus h times x. So we're x times x plus h. So we can distribute that x now. So we're going to have minus 3 over x squared plus xh. So that is the simplest form that we can rewrite this different quotient. Okay, moving on to number 6. Same problem. Difference quotient. So put that up here real quick, just like last time. And so we're just going to sub in the x plus h for the first one. So 3x plus h plus 6 minus, and should be just plugging in the original equation. Do I need the parentheses? Let's just put in 3x plus 6. And I actually do need the parentheses. and then this is all over h. So the next thing I'm going to do is distribute out this 3 on the top, this first one. So I'll end up with, excuse me, 3x plus 3h plus 6, excuse me, plus 6. Now I'll distribute this -1, so negative 3x minus 6. And this is all over h. Now the 3x and the minus 3x, those will cancel out. The 6 and the minus 6 will cancel out. And then, of course, this h will cancel out, which will leave us with just 3. So last one for these types, can't even talk. Again, I'll write down this difference quotient formula here. Function x plus h minus the original function over h. Now I'm going to substitute this x plus h for all the x's. So I have x plus h squared minus 5x plus h. And then that's all um, minus the whole original function, which is x squared minus 5x. All right, so first thing, let's sort out this x plus h squared. So, oh yeah, and all this is over h. So again, let's sort out this first part. I'm going to do x plus h and x plus h. That's going to give me x squared plus 2xh plus h squared. There we go. All right. So we'll take this whole thing and we'll put that in for this first section over here. So I'll rewrite that right here. So x squared plus 2xh plus h squared minus the 5, and I'll distribute this -5 over, so it's going to be minus 5x minus 5h, and then minus x squared plus 5x. There we go. And that's all over h. So this x and this minus x squared minus x squared, those guys cancel. This minus 5 and this plus 5, minus 5x plus 5x, those guys cancel. So now I'm left with 2xh plus h. I think this is supposed to be squared. Yeah, squared. I missed putting the squared up here. That's important. Minus 5h all over h. Well, this h can cancel. Oh, man. This h can cancel out, and one of those h's will be gone, and this h will be gone. So we'll be left with 2x plus one of the last h's minus 5. So that's a simplified form of that guy. All right, so for number 8, we just need to graph these functions. We kind of have two functions here. So let's look at the negative x plus 2 function. Really, this is y equals mx plus b, so it's a line. And the m is, in this case, is equal to 1, or -1, rather. So there's the negative right there. And we're transitioned up 2. So, and we also have this x is less than 0. So we're here at 2. And since this is slope is -1, it's going to be kind of going off this direction. And like I said, we have this x is less than 0. So we only have this side of the line. The line starts on the y-axis and it goes to the negative direction and does not go on the other side. Now a normal square root function would be graphed somewhat like this, and we are transitioned up 3, so let's just move the start point up 3, and there you go. There are the graphs of those two functions on the same graph. So I actually made a little bit of a mistake here. If you look at this top one here, its x is less than 0. So since it's not less than or equal to, there's actually a hole at the 0, 2 location. So this is just a less than only, not a less than or equal to. So there's technically a hole here. So actually, if I just erase the old line there, we'll erase this. Oops, erase too much. Put the tick mark back on there. All right, so there is a circle, an open circle here, and then it's our slope of our line, 1, 1 over -1, -1. So there you go. That's the correct line for number 8. Okay, for these next 3, we're going to determine, without graphing, whether the given quadratic function has a max value or a min value, and then find that value. Well, this is a parabola. And since it's a positive at the beginning, it is a parabola, I can't even speak, that opens up. So, opens up. So, it has a minimum value. So, the parabola opening up means it has a trough at the bottom, so that's where it'll have a minimum, right? Now, remember that x in this equation is going to be equal to negative b over 2a. Oh, gosh. Negative b over 2a. There we go. So our b value in here is 2, and our a value is 4. So we'll just, I got those from these parts here. And we'll just plug that into this little formula we have here. So negative 2 over 4, I'm sorry, 2 times 4 gives us negative 2 over 8, which actually is negative 1/4. So now, what do we do? Well, we're going to plug that back into the original formula. So we have 4 times the quantity negative 1/4 squared plus 2 times the quantity negative 1/4 minus 1. All right, well, negative 1/4 times negative 1/4 is going to be positive 1/16. And that's going to be times 4 anyway, so I'm just going to go ahead and do that here. 4 over 1, that's going to be 4 over 16, which ends up being 1 over 4. A long way to get back to just changing this sign. So anyway, that's this section. Now the next section is 2 times negative 1/4. So 2 over 1 times negative 1/4. That's going to be negative 2 over 4, which is equal to negative 1/2. So this is plus a negative 1/2 minus, oh, sorry, minus, let's try that again, 1. There we go. Now we need common denominators between all of this stuff, and it looks like it's going to be 4. So I'll do 1/4 minus, because a plus minus is really a minus, 2 over 4, minus another 4 over 4, which would be 1, right? So 1 minus 2 is negative 1, minus another 4. That is going to be negative 5 over 4. So that is the end of that problem. It's pretty simple. Let's rewrite this as the minimum is negative 5 over 4. So there we go. That's that little guy. Moving on to number 10. Basically going to do the same thing. And again, we have a, gosh, I'm having so many problems here. Parabola that opens up again. Opens us. Why do I keep writing us? Anyway, it opens up. There we go. So, oh, maybe I'm writing the S from the so. I'm getting ahead of myself. Anyway, so it's going to have a minimum again, just like the last problem. And just like the last problem, we will use this x equals negative b over 2a, which when we substitute in our numbers here, we have negative 3 over 2 times 3, which gives us negative 3 over 6, which is equal to negative 1/2. Now I substitute back in the negative 1/2 in for x to find my y value, which is my minimum. So 3 times the quantity negative 1/2 squared plus 3 times negative 1/2. Now 1/2 squared is going to be 1 over 4. So 3 times 1/4 plus negative 3/2. So 3 times negative 1/2. That's going to be negative 3/2. So this is 3 over 4 minus, because that negative and a plus is going to be changes to a minus. So 3 over 2. Get common denominators, which is going to be 4. So this will be 6 over 4. So this will equal negative 3/4. So write that over here as our minima. Minima is equal to negative 3 over 4. And there's number 10 done. Number 11 is just as easy, except we've got this negative out front. So we have a parabola that opens down. At least I won't write us this time. Anyway, since it's negative, it opens down. So this one has a maximum or a maxima. So again, we'll still use the negative b over 2a to find our x. So let's put in negative 10 over 2 times negative 5. And this 10 is negative as well. We've got all kinds of negatives here. Oh my gosh, what to do? Anyway, so we have negative 10 over negative 10. These negatives kind of cancel each other out, and we're left with just one negative. So we have negative 1. So we will substitute negative 1 in for x in this equation. So, of course, we have negative 5 times negative 1 squared minus 10 times negative 1. So we reduce this down. So negative 1 squared is 1. So we're in it with negative 5 here. And 10 times negative 1 is negative 1. So this is going to cancel and make it a plus. So plus 10. So this whole thing is going to equal 5. So our maxima is equal to 5. And that's number 11 done. So for these next three problems, we will use the graph to determine the domain and range of each function. Well, domain is everything going, from the left to the right. This defines our range, and it almost appears that we have negative infinity, because this little arrow here, and this little arrow over here. And so it looks like we have negative infinity to infinity. But there is this little asymptote here So that is not correct. So the asymptote is at 2. So our domain is set that x such that x cannot equal 2. So basically it's everything except for 2. Now our range is everything vertical, but again we have an asymptote. So, and it's at 3. So y such that y cannot equal 3. So that's how we find the domain and the range of that guy. Fairly simple. Number 13, probably just as easy. We can see that we have this, we're going to get our domain and our range here. Domain is such that x cannot equal -4. It's because we have this asymptote right here. Now notice our range is basically everything above the x-axis. So we'll just write our range as y such that y is greater than 0. And that's number 13. Number 14. This one gives us a little bit more of a curveball, but oh, the domain is going to have two asymptotes. So x such that x cannot equal this -2 and this 2. So I'll write that as x cannot equal -2 or x cannot equal 2. It cannot equal either of those. So really I guess I should have put and. But anyway, and our range, well, if we look in the middle section, we have this cotangent function here, or negative tangent, either way you want to look at it, and it goes forever in both directions. So our range is -infinity to infinity. So that's that guy. Okay, for number 15, we are going to graph the function. Well, we have a really ugly function here. So x squared over 1 plus 9 over x. Common denominators means we're going to have to get an x over on the other side. So we're going to end up with x to the third plus 9 over x. That's how we would get the common denominators. Now, since we have x in the bottom, x is missing on this side and the 1's missing on the other side, so this makes this x over 3. I'm sorry, x to the third over x plus 9x. But anyway, that's how I got that 3x plus 9 over x. I'm going to need this space, run out of space on this one for sure. But anyway, also, our instructor said that he's going to take this off our review. It's not going to be on our tests, so, but I'm going to do the problem anyway. So since x is in the denominator, x cannot equal 0. So we're going to have like this vertical asymptote here. Now, for this crazy function, apparently it's going to come up for us in Math 3A. And we're going to, or in calculus somewhere. So we'll know how to figure this out without having to do what I'm doing right here, which is doing an XY chart, because I don't really know any other way to do this. So I'm going to plug in 1 and find out what my y value is. So 1 to the third plus 9 over 1 is going to be 1 plus 9 over 1, and that'll be 10 over 1, which is 10. So if I input 1, I get 10. Now, how am I going to plot that on this graph? Let's just change all these to a multiple of 10, because this graph is going to be crazy. All right, now we have multiples of 10. You can't really tell where 1's going to be. It's going to be so close to the 9, but anyway, oops. me graph this first one. Or actually, let's do negative 1. Let's see what negative 1 gives us. So negative 1 to the third plus 9 over negative 1. Well, negative 1 times negative 1 times negative 1 gives us negative 1. Plus 9 over negative 1. That is going to give us 8 over negative 1. So that'll end up being negative 8. So negative 1 yields us negative 8. Okay, well, we're getting some weirdness here because we are, see if we graph 110, we're going to be somewhere here. And if we graph negative 1, negative 8, we're going to be somewhere here. Well, obviously, those are on opposite sides of this asymptote. So let's start plugging in some more numbers and see where we get. So 2 to the third plus 9 over 2 is equal to 2 times 2 is 4 times 2 is 8 plus 9 over 2. So we have 17 over 2. So if we have an x value, we as an input, we get 17 over 2. Well, that's going to be 8 point something, 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 something. Since my graph isn't super accurate, I'm not going to bother going much further than this. So let's see, where would that be? Just be a little bit over here and a little bit down here. So it's a little bit lower than our 110. Let's try 3. Let's see what happens with 3. So 3 to the third plus 9 over 2. 3 times 3 is 9, times 3 again is 27, plus 9 over 2. So that will be 36 over 2. And half of 36 is 18. So I can see that if I put in 3, I'm going to get 18. Well, 18 is a lot higher than when I put in the 2. So I'm going back up. So coming from this 110, and I know it's got to hug this asymptote. So this side of the equation is going to be looking something like this. It's going to go on forever, of course. But what about this other side? I have this other point over here. So let's try negative 2. Let's find out what's going on the negative side. So negative 2 to the third plus 9 over negative 2. Well, that's going to give me negative 8 plus 9 over negative 2. And that is going to be 1 over 2. So negative 1 half. So for an input of negative 2, I get an output of negative 1 half. Well, that's going to be somewhere up here. I mean, the resolution of my graph is not great, but it's definitely higher than my last negative, which was negative 1 and got negative 8. So it's closer to my x of 0. Well, what happens? Let's find out where it actually intersects the x-axis. So we'll set this y value to be 0. So 0 equals x to the third plus 9 over x. Well, oops. X times 0 will end up being 0. So that ends up being x, I'm sorry, 0 equals x to the third plus 9. Now I'll move the 9 over, so I'll get negative 9 equals x to the third. And then the third root of negative 9, all right, and my calculator says that this is equal to negative 2.08. So the x value is negative 2.08. Well, that is kind of like right over here. I know that would be like negative 5, but it's really hard. Anyway, I'll connect those 3 dots, and you can see that this is kind of veering off this way. So there's graphing that mess. All right, so hopefully this one will be a little bit better than the last one, although it doesn't look like it just looking at this. But anyway, we've got to find a few things before we can graph this guy. We're going to need some x-intercepts. We're going to need some y-intercepts. We're going to need a vertical asymptotes. We're going to need some horizontal asymptotes. And then if we don't have any of those, then we'll have to have these, I think it's SA. What does SA stand for? Side asymptotes or whatever. Oblique asymptotes, I think, is what they're really called. But they're the ones that go at an angle. So let's figure out this horizontal asymptotes first, because that's pretty easy. Let's see if our numerator, where do I want to write this? I'll write it over here. So if our numerator is equal to our denominator, and I'm talking about the exponents here, that means our asymptote is a ratio between the leading coefficients. Now, if our numerator is less than our denominator, that means our asymptote is just y equals 0. And our last possibility would be is if our numerator's exponent was greater than our denominator's exponent. And in that case, there are no asymptotes or horizontal ones. Now we have 2 and 2, so they are equal. So that means it's a ratio between our leading coefficient. And our leading coefficient in this case is 1 and 1. So the ratio there means we have a horizontal asymptote at 1. So I'm reversing back over here to get rid of these so we can see our original equation here. But anyway, horizontal asymptote is going to be 1. So to figure out any of the rest of this, really, we need to factor both the numerator and the denominator. So we have to fully factor everything. So let's factor our numerator. And, well, that's going to give me 5 and 6 will give me 30. And if I'm at 5, is it negative 6? No, because that would give me negative 1. So this is going to factor to x minus 5. Get rid of this crap up here. And x plus 6. That's my numerator. And now I need to factor my denominator. So x squared minus x minus 42. And that is going to be, again, I'm going to have an x minus, and I'll have an x plus. And so what's it going to be? Well, since we have minus minus, that tells me I'm having opposites, so the bigger one should be the negative. And let's see, the bigger what? 7 times 6 gets us to 42. So the bigger number should go in the negative side, and the smaller number, wish I would have remembered that when I factored the numerator, because I was stumbling on that a little bit. But anyway, it's all coming back to me. All right, we'll just write that again under here as our denominator. There we go. So if we look just at the denominator, we can see that our zeros, the things that would make this 0, are 7 and negative 6. And remember, we can't have the denominator 0 because that would make it undefined. So that's why it's important to find these. But we can see that this x plus 6 is in the numerator and the denominator. So those would cancel out. So, but we can't just cancel out this. This x equals negative 6 is going to be a whole. Oh, battery running out. So I'm going to just write that down over here. Wait, not 7. Let's put x equals 7 and at a whole at negative 6. just so I remember when I start going graphing here in a little bit. Now let's find this x and the y-intercept. Find the x-intercepts. I set y to equal 0, so basically setting the whole equation to equal 0. And I'm just going to deal with the part after I canceled out those two bits, so it's easy. Well, if I multiply both sides by x minus 7, I'm going to get x minus 5 is still equal to 0. And then x is equal to 5. So I only have one x-intercept here, and it's going to be at 5. Now, if I want to find my y-intercepts, I set x equal to 0, and that would give me negative 5 over negative 7, and that equals y. And the negatives cancel out, so I have 5/7. That's my y-intercept. And now it's time to start plotting and graphing, because I have all the information I need. The side asymptote thing, or the oblique asymptote, we're not going to have it because we have horizontal ones. So our vertical asymptote, that's 7, and I'm going to have a problem here because my graph is not quite big enough. So let's change the resolution of the graph just by changing these numbers. I don't have space to make it bigger, so we'll just make these twos. So 2, 4, 6, 8, 10, 2, 4, 6, 8, 10, and then draw on the negative ones here. And 4, 6, 8, 10, negative, 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 negative. There we go. All right, so back to asymptotes. There's one vertical one here at 7, and I'm going to have a hole at negative 6, but it's going to be somewhere in here. So I just got to remember when I'm graphing that there will be a break here. Now my horizontal asymptote is at 1, so I'll just draw that guy in here. And get rid of this little hole thing because the hole's going to actually be small below that line. I don't know exactly where that hole is on the y-axis, but I know it's right above the 6. So anyway, my x-intercept is going to be at 5, and my y-intercept is going to be at 5/7, so somewhere here-ish. And my hole is somewhere here. It's not a very good hole, it just looks like a point. Let's get this to be very, very thin lined. There you go. Now it looks like a hole. And we'll go back to a bigger weight pen, and we can draw boop, right up to the hole, and then on the other side of the hole, and connect to the 5, and there you go. It's going to go all the way down. All right, so our other bit is going to be in this quadrant here, and there you go. Bob's your uncle. We have graphed this nasty little piece here. All right, so we'll be moving on to number 17. And in these next couple of problems, we'll use the rational zeros theorem to find all the zeros of the polynomial function. Use the zeros to factor f over the real number. So this basically means that we're going to be using synthetic division. So we look at the beginning and end. So this 25, we factor it down. We can see that we have three factors. We have 1, 5, and 25. So we're going to note those down onto the side over here, 1, 5, and 25. Then we'll factor the leading coefficient, or leading term. There's only two, so 1 and 2. That goes on the bottom here. And basically, remember we have to make this list of all the possible solutions to make zeros. So it's plus or minus 1, 5, 25, and then 1 over 2, and 5 over 2, and 25 over 2. Technically, it's 1 over 1, and then 5 over 1, and 25 over 1, but that's where we get the 1, 5, and 25. So I'm going to need some more room here to do synthetic division, and I'm going to move our possibles over here. And I already worked this out earlier, so I know some of the answers, but I'm going to show you the process. So we're going to take these leading parts of all these terms. So we'll bring down this 2, negative 20, 51, negative 10, and 25. And like I said, I'm going to try some of the ones that don't work, and then we'll get to the ones that do work, and then we'll kind of skip testing all the other ones. So we'll move this 2 down, and we'll just try the first one as a positive. So we'll do positive 1. There we go. 1 times 2 is 2. Add those together, we get negative 18. Multiply 1 times negative 18, we get negative 18. Then we are going to add those together, and we're going to come up with, what are we going up with? 33. Yep. So 1 times 33, and then we add those together, we're going to get 23, and then obviously this does not make a 0 at the end. So failure number 1. So then the next thing we try is negative 1. So we get negative 2, and then that put together is negative 22, and then times 22, and then that adds together 73, and then that becomes negative 73 and negative 80. This is obviously not going to work because negative 1 times negative 83 is 83, and that's not going to make it 0 over there. So how about we try our 5? So 5 times 2 is 10, so that's going to add together and give us negative 10. And then that multiplied together is negative 50, and that added together is going to be 1, and 1 times 5 is 5. Negative 10 plus 5 is negative 5, and 5 times negative 5 is 25. Yay, it's a 0. So we found our first 0, and this is for our fourth exponent. So 0 would be x minus 5. And since this is to the fourth, I'll just write that here just to remind myself. So now I'm working on to the third power. So technically, we just continue to do this again, but we'd start all over with our zeros. We'd start with our 1. So positive 1. We multiply that all through, blah, 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 and that's not going to be a 0. Trust me. We'll do it again with 5. Let's just jump ahead to 5. 5 times 2 is 10, so that becomes a 0. And that's 0, so I get 1. And 5 times 1, well, that's a 0. So then we've found another 5. Now, notice these are the same 0. I just basically found the same 0. So this is actually x minus 5 squared. So, because we got 2 of those. Now, since this is to the second, it's a lot easier just to put this, would be 2x to the second plus 0x plus 1. So we can just write that down here. 2x, and there's no 0x plus 1. So this is our, oops, forgot my exponent here. And so I can just rewrite this whole thing to x to the second plus 1 times quantity x minus 5, and that quantity squared. So that's our final answer for number 17. So for number 18, we pretty much have the same type problem. So I just need to find all my factors here so I can create my list. So this one, I'm on the top, I'm going to get 1, 3, and 9. And on the bottom, I have 1, 4, and then 2 and 2. So 1, 2, and 4. So 1, 2, 4. So that gives me a plus or minus 1, 3, 9. Get rid of some of this stuff here. I'm kind of lazy, and I write this as plus minus, and I just do a bracket thing. But anyway, 1, 3, and 9. And then that takes care of this 1 on the bottom. So then my fractional parts is going to be 1/2, and then 1/4, and then 3/2, and then 3/4, quarter, and then 3 halves, or sorry, 9 halves, and 9 quarters. I just put my squiggly line around here, so it's plus or minus any one of those in the list. Otherwise, you have to write plus or minus, plus or minus, plus or minus, plus or minus. I don't want to do that. I'm lazy. So now we know all of our possibles. So let's start our synthetic division chart here for -11, -6, +9. And then we bring down the 4, of course. I'll grab a different color. Let's go with blue. We'll do our 1, and we'll do the +1 first. It gives me 4, so this is going to give me -7. So -7, and those together is -13. And -13 plus 9, obviously not a 0. What a bummer. All right, well, let's try -1. -1 times 4 is -4. That's going to be -15. -1 times -15 is positive 15. Sorry. And that's going to give me 9. And 9 times -1 is -9. Yoo-hoo, a 0. So x plus 1 is one of my zeros. And this section was our exponent to the third. But we'll go down another level. So we'll bring down our 4. Technically, we got to start all over with our 1. So 1 times 4, that's going to give me a -11, and then that's not a 0. So then we try -1. And that is not going to be a 0. So I'm just going to skip to 3 because I know that that one's going to be a 0 because I did the problem earlier. So that gives me -3, and then -3 times 3 is -9. That gives me a 0. Now remember, that's going to be x minus 3 is my 0. Now this top part, the 4, 11, -6, 9, that was my exponent to the third, and this is my exponent to the second. So this down here would just be my x. I wouldn't raise it to any power here. So this is 4x minus 3. So 3/4 would be a 0. So these are all of my zeros. I can rewrite them. 4x minus 3 is a quantity, and then x minus 3, and then x plus 1. So there you go. Now, the directions only say to do this much, but our instructor said, well, you might have to sketch this graph. So what would you do if you had to sketch a graph of this? Well, let's just do a little side work here. And this is our original function here. Forgot to put my f of x here, but this is the original function. And we found our zeros, which was this portion. So I can just write our zeros down here as -1 is one of them, 3/4 is another, and 3 is another. So all of those would make this whole thing 0. So I can plot these points. There's -1, 3/4 would be about here, and then of course 3 would be here. So that's where it crosses the x-axis. Now all of these are multiplicity of 1, and that's an odd number. So an odd multiplicity means the line is going to cross the x-axis. So multiplicity means crosses the x-axis. If they were even, for example, if they were squared or to the 4th or 6th or whatever, that means it would bounce off of the x-axis from whichever side it was on at the time. So evens bounce, just in case we get something different on the test. Now our leading term is positive. So since it's positive, our function is going to end in a positive fashion. So it's going to end in quadrant 1, basically. Gosh, I can't write or spell right now. So it means it ends positive. And my penmanship's terrible. So we have the trifecta of horrible writing. So I start here, but really this is where the line ends, right? So we start at negative infinity and we move towards infinity. So this is where it ends. It's going to end positive. So, but as I said, I start here, so I make sure I get my right bounces and crosses. So this is basically what our graph would look like for this. So there you go. So 19, use the given 0 to find the remaining zeros of the function. Well, that's nice of them. They gave us a 0, -4. So we can start our synthetic division, and this will be 1 minus 2 minus 11, and our 52. And basically, we're just going to use the -4 right off the bat. We don't have to do all this factoring stuff. So this will be -4, which will equal -6. -4 times -6 is 24, so that's going to be 13. Added together, of course, and then -4 times 13 is -52. And this should be no surprise. It was given to us that this was a 0, so it should work out to 0. And since that was to the third power, all this down here is to the second power. Since I didn't factor out, I could have looked for more zeros doing the other method, but we'll go this way because there are no other zeros. I already know. And this isn't factorable. So remember our quadratic equation here that I'm rewriting here for AC over 2A. So our A is 1, our B is -6, and our C is 13. So I just substitute all this into my quadratic equation so I can get the rest of my zeros. So -6 squared minus 4 times 1 times 13 all over 2 times 1. All right, so now let's start simplifying this. A -6, -6, that's just going to turn into 6, +6. Those negatives cancel out. This will turn into 36, so plus or minus square root 36, minus 4 times 1, which is 4 times 13, which is 52. We already did that math. Then this will be over 2 times 1 will be 2. So 36 minus 52 is going to be a -16. Yeah, -16. So this is going to be 6 plus or minus the square root of -16 all over 2. Well, -16, well, 16, the square root of that is 4. So, but since it's negative, it's going to be 4i. So that's imaginary over 2. And then, of course, we can reduce this to be 3 plus or minus 2i. So our answer is 3 plus or minus 2i. Our instructor, I think, is still okay with us writing it that way, but if you have somebody else that makes you write them out, well, you separate them. So here are 2 additional zeros for this problem. All right, for number 20, let's find our possibles. We got 2 and 13 here, plus or minus 2 or 13. And since we have a 1 here, that's all of our trials that we're going to need to do is 2 and 13. Now they were nice enough to give us one of the zeros, so it's 3 plus 2i. So that means its reciprocal or conjugate is also a 0. So really we're just going to have to find one more 0. So I'll write down our synthetic division here. 1 minus 8, 25 minus 26. Bring down this 1. And let's try 2. We'll plug in 2 here. 2 times 1 is 2. So adding that together, it's going to be -6 times 2 is -12, which is going to give us 13. 13, and 2 times 13 is 26. That cancels that out. Woohoo! We found another 0. Now, this means we found all of the zeros, basically. Because remember, this multiplicity of the leading coefficient tells us we have 3 possible zeros, up to 3 zeros. So we got 3 plus 2i given to us, which means 3 minus 2i is a 0. And the one we just found, which is 2. So there's our 3 zeros. We cannot have any more than that. We could have less, but not more. So there you go. 21, it's the same thing. So we only have 2 possibles here is 1 and 13. But over here, I'll put that here, 1 and 13. But our leading coefficient also have 2 possibles, which is 1 and 3. So that means we have to have 1 over 3 and 13 over 3 as pieces that we need to try. So we already have 3 plus 2i, so that means we have 3 minus 2i as well. However, we have a multiplicity of 4 for our leading coefficient here, so that means we have a potential of 4 zeros. So we have to keep trying till we either use up all of our possibles or we find 4 zeros. So set up our synthetic division here, 3, and we're going to bring that 3 down. And so negative 22, 64 minus 58, and 13. So we're going to try 1 first. We'll try the positive 1 first. So we get 3, then negative 19, negative 19. Add that together, we get 40. What do we get? 45. Yeah, 45. Add that all together, and we get negative 13. 1 times negative 13 is 15, and this is a 0. So we can add that to our list here, 1. And now add our commas, because we could potentially have one more, but we don't know yet until we try everything. So we'll bring down our 3, and then technically, whoops, sorry about that. Technically, we would start with positive 1 again. So we'd go through this whole process, and that's not going to be a 0 because I've already tried it. And in the interest of saving time, I'm just going to kind of burn through these. But then we try negative 1, and that's going to not work. So then we'd come to 13. We try that one. And that one doesn't work. Neither does negative 13. So let's try 1/3. So 1/3 of 3 is 1. And so that's going to give us negative 18. 1/3 of negative 18 is negative 6, which is going to give us 39. And 1/3 of 39 is going to give us 13. And lo and behold, we have another 0. So 1/3 is one of our zeros. So we found 4 zeros, and our multiplicity is 4. There's no way that we can have any more, so we're done. All right, so for the next one, we write as the sum and or difference of logarithms. Can't talk. Express powers as factors. Well, there's some parts that we need to recall here with logs. So log a, or sub a, m times n, can be rewritten as log base a m plus log base a n. So if they're multiplication, they can be rewritten as a addition. Then log base a with m divided by n, that can be rewritten as a subtraction. So it's log base a m minus log base a n. And then the last rule that we have with logs is log base a m raised to a power of r, for example. Oops, give me my arrow here. Can be rewritten with the exponent out front, so r log base a m. Now, knowing these 3 rules, we can rewrite this as a sum and or difference. So since it's a division, we'll start off by doing this part of it. So we have log base 9 and the 8th root of 17. And that's one portion. And then we'll do the, so since this is one portion, the bottom is the second portion. So we'll do log base 9 s to the second. And since in the bottom we have this multiplication thing going on, that is like our first rule that's up here. So I'm just going to say plus log base 9 times r. All right, so the reason I put these in quantity bits is because now I can deal with those individually. I can change log base 9. The 8th root is really saying 17 to the 1/8, right? And looking at our third rule, anything that's log base something raised to a power, we can move that power out in front. So I'm going to put 1/8 log base 9, 17. So I've dealt with this first quantity. Now minus, and I'm going to basically distribute a 1 across here. So log base 9 s, but I have that exponent. So whoop, let's use that third rule again. We'll move that 2 out front using this third rule here. So we'll do minus 2 log base 9 s. Now remember, I'm distributing this negative to each of these. It's negative 1. So this means now this turns into a minus, and then log base 9 r. So that's our final answer for this one. And moving on to the next. Moving on to number 23. Express as a single logarithm. All right, so notice we don't have everything in terms of log a, but recall that log a can be written as a to the nth. So if we change this 2 to a to the nth, it would be 2 to the, or a to the second. So we can rewrite all of this as log 3 log 8 quantity 2x plus 1 minus log 2a quantity 2x minus 1 plus log a to the second. And that's this portion of it. So now we can use our other rules dealing with logarithms. So I'll deal with this one first. I can move this exponent over. So I have log a and then quantity x to the, or sorry, 2x plus 1, and then that's cubed. And just moving these 2's that are out in front to the exponent location, basically. So then we have log a times the quantity 2x minus 1 to the second plus log a squared. All right, so now let's combine these first two terms, or first two sections rather. And since it's a subtraction, it means it's going to turn into a division. So what I'm going to do is put log a, and then I'm going to put the first term's bit on top of the fraction, and the second term's bit on the bottom. So write it just like this. X, whoa, there we go. X minus 1 squared. There we go. And this plus log a, or base a squared. Now, since this is a plus section here, I'm going to multiply this. So really I have a squared over 1. And so that means I'm just going to put a squared times this upper part, or the numerator. Don't forget the cubed. And then The bottom part is times 1, so it just remains the same. And there you go. Bob's your uncle. We have finished number 23. Let's get a better box here. There we go. And now 24. They give us something that looks really nasty, but the first thing that we need to look at here is factoring all of these bits so we can properly reduce this. So we got to factor all of this stuff. So I'm going to go kind of quickly on this in the interest of time, but I'm going to write this first one ln, and I have x. It's going to be, factor this is going to be x plus 7 minus 2, so x minus 2. There we go. And that's going to be over that quantity x minus 1. And since this is a minus, when I combine it, it would be a fraction, but I'm going to change it to a multiplication. I'm going to reverse this, flip it over. So I'm just going to put this one on the bottom here just to make it quicker. So x plus 7 times the quantity x minus 1, that'd be factoring the numerator, but I'm putting it in the denominator. And then putting the denominator in the numerator, because this would be, as I said, a division, but then we multiply the inverse, right? So if I combine this, I can see that the x plus 7's cancel, which is great. So now I have, let's see, x plus 2, and then x plus 1 all over x minus 1, and this is squared because there's 2 of them. Now I add my next part, and I'm going to difference of squares there. So that's x minus 2 squared. Is that plus? Wait a minute. I have messed something up here. That should be minus. But this guy should be minus as well. That's where I messed up. I knew I was going to have to combine something else in this problem, so glad I caught that. Anyway, so this is, since there are 2 ln's, it'll be a multiplication. So it's going to end up being, there's a 1 here and a 2 there, so there's 3 of these, so I can combine them. So the quantity x minus 2 is cubed times x plus 1. And then, of course, my denominator is x minus 1 squared. And that is that guy finished. So for number 25, we use transformations to graph the function, determine the domain, range, and horizontal asymptote of the function. So let's just look at f of x equals 2 to the x. That would just be a standard exponential function, an asymptote of right along the x-axis, and this would just basically look like this. I'm going to take that away because we're going to graph something else over it. So in a normal function, we'd have x and y's. Let's just choose some easy ones, 0, 2, and 3. So if we plugged in 0 to this regular function, we'd get 1. So there you go. If we plugged in 2, we'd get 4. If we plugged in 3, we would get 8. So those would be our standard points for this type of exponential equation. So the reason I'm doing it this way is because we're supposed to use transformations. So I'm going to transform these points. Another way you could do the transformations is knowing that the negative is going to reflect, and then do that, and then move the graph up 4 and then left 3. And it's kind of a big pain to do all of that. So I'm just going to do it mathematically with these points. So if we look here, this would be our graph of a 2 to the x. Let's see, and then the 8th would be like off our graph way up here. So whoop, that would be a standard exponential notation, and this is be our horizontal asymptote right here, the x-axis. But as I said, we're going to transform this with all this extra busyness around here. Let's see if I can get rid of all these points. There we go. All right. So what? Let's since we're doing transformations, we'll do the reflection first. That means we're going to get a graph that goes down like this, and then we're going to move it up 4, so then it'll be something like this, and then it'll get shifted over 3. So we'll take those away. So we kind of know what to expect. So since we are reflecting, well, this is our horizontal asymptote. It's going to go up 4. So that goes up 4. And the up 4 affects our y. And actually, to be technically correct, we should do the reflection first. So let's just do that really quick. Our reflection reflects, and that reflections, can't write today, reflections affect the y value. So if it's a positive, it goes to negative, and if it was a negative, it goes to a positive. That's how reflections work. And since we're, in this case, reflecting over the x-axis, we're just going to change the sign of the y of our ordered pair. Now that takes care of the reflection part of it. Next, we're going to look at our horizontal asymptote. It got moved up 4, but everything else gets moved up 4. And we're moving up and down. We're affecting the y portion again. So we affect the y again, but this time we are going up 4. So we're effectively adding 4 to the y component. So if we do that step, we're going to get 0, -3, and then 2, 0, and then we'll get 3, comma, -4. So I've just added 4 to all the y parts of those ordered pairs. Now the last step is this little translation horizontally, and it's +3, so that's going to affect the x -3. We're going to subtract 3 because it was a plus on the in the formula, but we change it to a minus. It does kind of the opposite effect. So we go 3 to the left. So it's -3 or 3 to the left, however you want to think about it. But I think about it as -3 because that's, I'm going to subtract 3 from all of these x's. So -3, comma, -3, and then -1, comma, 0, and then 0, comma, -4. Now you might have guessed why I chose those original blue numbers, because it comes out kind of nice here. So what I'm going to do next is just plot those numbers. So here's our -3, 3, and then we'll go 1, 0. It's going to be right here, and then 0, -4. It's nice that we have the x and y intercepts. And remember, this is our horizontal asymptote. For you get your full credit, you're going to need to draw that guy. So I'll just sketch that guy. Besides, you need to know where this line kind of hugs along, because it's going to hug along just like so and go through all these points. And there's your line. But wait, there's more. Oops, sorry about that. This problem asks you to determine the domain, range, and the horizontal asymptote of the function. So our domain, as we can see, starts at -infinity and keeps going to infinity. So we have -infinity to infinity. Our range starts at -infinity and it goes up to, but does not include 4. So that was our vertical or our horizontal asymptote. So we might as well write that here as well. Y equals 4. And that's the answer to this problem. So for this next 3, use the given information given to find the exact value of the trigonometric function. Now, theta lies in quadrant 2. And our theta is in the terms of secant. So I can change that to cosine by inverting this. So it would be -3/5. So since it's in quadrant 2, I'll draw that here. So we got negative 3 over 5. So that's the negative 3 goes here, and the 5, is, of course, is the hypotenuse. And then we need to know y. But do we need to know y? Don't think we need to know y, because sine, half angle identity for sine is plus or minus the square root of 1 minus cosine theta over 2. So we don't even need to know what y is, so we don't need that. So, 2, we can just plug our cosine into this equation. And we're going to deal with the positive part because sine is positive in quadrant 2. So, 1 minus negative 3 halves, or sorry, 3/5 over 2. So, what should I do next? I'll just multiply by 1/2. So I get 1/2. Um, going to be plus 3/10. Now remember that subtracting a negative turns this into a positive, right? So that's where I got the plus from there. When I multiply the 2 times the numerator, or the denominator, here's this part of it, negative 3/5 times 1/2, that gives me a negative 3/10. Remember these two negatives here cancel each other out, make it a positive, so that's where I get the plus 3/10. So now that we've got that all sorted out, kind of running out of room over here, so I'll bring this over here, and at the same time I'm going to get common denominators. So the 1/2 will turn into 5/10. There we go, plus the 3/10. And that is going to be equal to 8/10. So the square root of that, which is equal to 2 square root of 2 over the square root of 10. Now where did I get that 2 square root of 2? Well, if I do square root of 8, that can be written as 2 times 4. So the square root of 2 times 4, well, square root of 4 is 2. So you get 2 square root of 2. So that's where that came from, in case you forgot. Now we need to rationalize this, so times square root of 10 over square root of 10. So that's going to give me 2 square root of 20. I'm going to put that, whoa, I'm going to put that over here. 2 square root of 20 over 10. Now this can be further reduced. So we have square root of 20 over 5. But square root of 20 can be reduced because 4 times 5, right? So square root of 4 times 5, and square root of 4 is 2. So this turns into 2 square root 5 over 5. And that is that guy finished. For 27, we're asked to give sine theta negative 21 over 29 lies in Q4. And we're going to find cosine half angle. So draw this in our quadrant 4. Make this triangle a little bigger. And 29 is our hypotenuse, so that's going to go over here. Whoa. And negative 21 goes right here because it's sine. Opposite over hypotenuse. All right, so we're going to have to find out what cosine is. So Pythagorean theorem, negative 21 squared plus b squared equals 29 squared. And quickly use a calculator really quick because I don't want to do long math on this one. All right, so this is 441 plus b squared and 841. Yep. That makes this part easy math. So b squared is equal to 400, and the square root of 400 is 20. So this is 20. So our cosine is equal to 20 over 29. Oops, 20 over 29. Now we're using our cosine half angle identity. So just write that down here really quick. Cosine half angle is equal to plus or minus the square root of 1 plus cosine theta over dos, or 2, for those of you who can't speak Spanish. So we're going to use the negative portion of this because cosine is in quadrant 4, but the half of that, it puts it in quadrant 2, so that's going to make it negative. So we got 1 plus 20 over 29 all over 2. And then that is going to reduce down to 1/2 plus 20 over 58, because 29 times 2 is 58. And then that is going to change to 29 over 58 plus 20 over 58. I'm going to move all this down over here because I'm running out of room. So that is going to be 49 over 58. And then we can split these radicals up so it's not under, oh yeah, this is negative, by the way. Keep carrying that negative around. We can split this up to 49, or the square root of 49 over the square root of 58. And then we can change this to negative 7 over square root of 58. Now we're going to have to rationalize the denominators. So square root of 58 times square root of 58. And not keeping track of my negatives here. Oh, wait. And now I'm getting negative happy. I don't need this negative. I just need it in front of the 7. All right. So now we're going to have negative 7 square root of 58 over 58, which is going to be our final answer. Yay! So on to 28. It's almost the exact same problem. It's just a little bit different numbers. We're given cosine this time, but we're finding cosine. So our cosine half angle identity again, cosine half angle equals plus or minus square root of 1 plus cosine over 2. Now, since they're giving us cosine and it lies in quadrant 4, this is where it's going to be. So it's going to be 4 over the hypotenuse is 5, and this is a negative y, but we don't really need that because we don't need to know what sine is to plug it into the formula. So we're going to use the negative portion because, again, half of this cosine is going to push it into the second quadrant. So we got 1 plus 405 over 2, and that's underneath the radical, and again, negative. And that is going to equal 1/2 plus 20 over, wait, 4 over 10. I don't even know what I'm talking about here. I'm still on the last problem. Anyway, and then that is going to equal negative square root 5 over 10 plus 4 over 10, because I'm getting common denominators within the radical here. So that, I'm going to put this over here, is going to be 9 over 10. And then, of course, that we can split up. So we have square root of 9 over square root of 10. And that's negative. And that's going to equal 3 over square root of 10. Of course, negative. Then we rationalize the denominators. So square root of 10 over square root of 10. Multiply them. Then we're going to get negative 3 square root of 10 over 10. Final answer. Now on 29, we are graphing this function. So this function is normally would be an exponential function moving up, But since we have this negative here, it reflects it across the y-axis. So we should expect to see some sort of graph that looks like that. Now, since we have this -1, our horizontal asymptote is going to shift down 1 from the 0. So I can just sketch that right now, kind of get that out of the way. So I know my line is going to hug that on the positive side to from infinity. It's very, very close to that line. I'm moving on. So let's try x equals -2. So 2 to the exponent negative of -2, which would cancel out. So 2 squared minus 1, which would be 4 minus 1, which would equal 3. So our ordered pair here is -2, 3. Now let's try another one, just so we can get a couple points on here. Doing this kind of quick. X equals 0. How's that? Now, anything to the 0 power is 1, right? So 1 minus 1 is equal to 0. So this is going to be 0, 0. Now, I have a couple points here. Let's go ahead and graph them. So we'll go -2 to 3, and then 0, 0, of course. And we can draw our line. I'll use green. And there you go, just as suspected. So after reviewing this with our instructor, he prefers to have 3 points. So I'm just going to add another point here. So x equals -1. So we'll sub in -1 for x. So we have 2 to the negative of -1 minus 1. So these two negatives turn into a positive. So 2 minus 1. And then we are going to get 1. So -1, 1. And we can plot that point. Wait, I used this color for the points. So that's where that would be. And it's already on the line, so I'm not going to redraw the line. So there you go. Make sure you have 3 points. That way you're accurate. These next couple will go kind of quickly, but just going to do an XY chart. And let's try 2. If we plug that into a calculator, it's a pretty easy one. It ends up coming to 2. We'll put in 4. That comes out to be 4. And let's try 1. And that will come out to be 0. So we end up with these 3 points. So we can go ahead and sketch those 3 points. So 2, 2 is here, 4, 4 is here, 1, 0 is here. And our vertical asymptote is this y-axis. So we'll just mark that. You'll need that to get credit for this problem. And here we go. That's number 30. Moving on. Number 31. I'm going to do exactly the same thing I did before, but I'm going to choose some strange numbers here based on the log 3. I'm just going to do things that are kind of multiples of 3 and see what happens. I'm going to start with 1/9 because I know it's a -1/2, so it's going to flip the thing and it's going to be a very steep angle. So we'll try 1/9, 1, 3, and 9. We'll plug those into our calculator and we should get some pretty easy numbers out of these. But just to double check, calculator says 1/9 will equal 1. 1 would equal 0, and 3 would equal -1/2 or 0.5, and 9 is going to equal -1. There we go. So we can plot all of these numbers. Let's get a smaller resolution dot here, considering I made our scale times 2. So there's 1/9 and 1, so it's not, I mean, it would even be closer to the x-axis than that, but here's, or not the x-axis, the y-axis. So there was 1, 0, and here's 3 half, and here's 9, 1. And our vertical asymptote is this guy right here. Just label it because it's hard to see. And then we'll connect the dots, basically hug this asymptote. Actually, let's go back to a bigger weight line and connect the dots, and then we can see that this is going to be really steep angles, just like I said. There you go. That's number 31. Okay, moving on to 32. Here we don't have the log base 2 out here, but we can change this to log base 2 and put 2 to the 4th. And then we can start changing some of this around. Since this is a subtraction, it's going to turn into division. So log base 2 with 3x minus 2 on the numerator and x minus 5 for the denominator. And that's going to equal log base 2 to the 4th. Now these logs, we can cancel those out. And that leaves us with the 3x minus 2 over the x minus 5 equaling 2 to the 4th, which is actually 16. So we'll cross that out and we'll make that 16. Now we have, if we multiply both sides by x minus 5, we end up with this guy, which is 3x minus 2 is equal to 16 times the quantity x minus 5. All right, come back over onto this side here, and I'll distribute all this out. So it's going to be 3x minus 2 is equal to 16x minus 16 times 5. 80? Let's try it. 16 times 5, that's 30. Yeah, 80. Sometimes I just don't trust myself. Anyway, I'm going to need this space. Maybe. I don't know. 80. All right, so now we can combine like terms. So I'm just going to kind of do this all. Well, I'll write it down. We don't need this quantity section here. But, whoops. Sorry about that. Anyway, so we got 3x minus 16x, because I'm moving that 16 over, equals 80 minus, I'm sorry, negative 80 minus 2. So, actually it's plus 2. Anyway, so this combines to negative 13x, and since that should be a plus 2, it's going to be negative 78. So x is equal to negative 78 over negative 13, which is 6. So moving on, we'll do number 33 here. We kind of have that same issue where the 3 doesn't have the log base. So we'll just change this to log base 3, 3 to the 3rd. So we have this all kind of done up. Now this is going to be a multiplication. So I'm just going to distribute this, factor it, unfactor it, however, whatever you want to say. It's getting late. Let's see. So plus 55 equals 27. 3 to the 3rd is 27. Yep. All right. So now I can start combining these like terms. I have x squared minus 16x and plus, let's see, 55 minus 27. Again, don't trust myself here. It's going to be 28. Yep, 28. So 28. And then all this equals 0. All right, so now we've gotten rid of the logs and made ourselves this quadratic, which can't be factored really. So we're going to be, well, I just unfactored it. But anyway, I'm going to use a quadratic equation to find out what x is. So this is the quadratic equation, in case you forgot. And we can see our A is 1, and our B is negative 16, and our C is 28. So I'm just going to substitute all those values into the quadratic equation. So I get negative b, which will be negative 16, which is going to cancel out, but plus or minus square root of negative 16 squared minus 4 is 1 and c is 28. So multiplying all of that. And all of this is going to be over 2 times 1, which will be 2. All right, so let's start consolidating this stuff down. And so negative of a negative is going to be positive, like I said. So it's going to be 16 plus or minus. We got 16 times 16, so that's 36, 6, 3, 9, 96, and this will be 16, so 6, 15, 20, I'm sorry, 256. So this is 256 minus 4 times 1 is 4, and times 28. It's going to be 112. Looks like. So over 2. And if we subtract these guys, we are going to get 144, which is nice because that's a nice even number that can be, we can find the square root of, or you should be able to by now. And that's going to be 12. So it's going to be 16 plus or minus 12 over 2. But all of this can be reduced. So this is 8, this is 6. Get rid of the 2. So we got 8 plus or minus 6, which means that our x is either 14 or it is 2. So we have two possibilities, but we need to check. So we got to look back into our original log function. And remember, a log can't be negative. So we can't have one of these terms be negative. So if we look up here, we have x minus 5 and x minus 11. So x has to be greater than that 11. So that eliminates this as a possibility. So our answer is x equals 14. So x equals 14, and that's our answer. So for number 34, or these next couple, we'll be determining the equation of the function that is graphed. So this is craziness. Y is going to be equal to sine, because I like to deal with sine. It's easiest for me to see. And some x value here. So 1, 2, 3, 4. 4 crossings of the x, 4 over the 2 at the 2 pi. That's here. So I'm really going to get 2 here. So it's going to be 2x. But notice sine is normally, and our amplitude is 1. So, but anyway, sine normal, whoops, let's back that up just a little bit. Sine normally looks like this, but we have the reverse of that. So sine is going to be negative in this case. So we have negative 1, but, whoa, craziness. Remember our identities that allow us to move this negative inside. So sine is equal to negative 2x. And that's this one. So for these next ones, we're going to graph the function over a 1-period interval. Okay, so interesting. We start out with a plus 3. So I like to deal with this right off the bat. So our axis of symmetry is going to be clear up here at 3. Done and dealt with. So the next part of this is we are going to look at what's on the inside here and find our period. So 0 is less than or equal to 2x minus pi, which is less than or equal to 2 pi. Our normal period is between 0 and 2 pi. I put what's happening to the x in the middle there. And now I'm just going to add pi to both sides to get that out of there. So now our period is between pi less than or equal to 2x, which is less than or equal to 3 pi, because I added that pi to both sides. Divide this whole thing by 2, and that is going to get us pi over 2, such that, well, it's less than or equal to x, which is less than or equal to 3 pi over 2. And so our period is going to be 3 pi over 2 minus pi over 2. So our period is actually 2 pi over 2, which reduces to our period is pi. Conveniently, we have our period set at pi over here already on the graph. Now our tick marks are going to be defined by pi divided by 4. So every 1/4 is going to be a tick mark. And again, conveniently, I've actually got this graph correctly before I started. So we're going to know where everything goes. Now the next part that we need to deal with is, where do these points go? So we've got to kind of look at this 1/3 here in front of the sign. And that means that I'm dividing between 3 and 4 into thirds. And that doesn't quite do it. So it's going to be closer to the half point there. And then the other third there, approximately. And then we're going to go with, that's about where the 3 pi over 4 would be. It's going to be on that third point, and then the pi, it'll be right on that new axis of symmetry. If I continue way out here past pi, this would be where the next point would be. Divide this lower section into thirds as well. And let's get, this is where this point would be, and we'd start, of course, on the axis of 3. So there you go. That would be a section of, actually, that's more than one period, so let's actually just draw one period. There we go. So that's one period. Okay, for number 36, kind of throwing us for a loop here. We just need to distribute this 4 out here. So we're going to get 4x minus 4 pi over 3. This is going to make this a very annoying problem. Kind of ugly, but we can do it. So we need to figure out our period, which is normally defined between 0 and 2 pi. So we'll put 0 is less than or equal to 4x minus 4 pi over 3. We'll put that in the middle. And less than or equal to 2 pi. First thing we're going to do is we're going to add 4 pi over 3 to both sides. So we end up with 4 pi over 3 on this side is less than or equal to 4x, which is less than or equal to 2 pi plus 4 pi over 3. Well, we're going to have to, oops, put a 4 in there, 4 pi over 3. Well, to get the common denominator of 3, I'm going to have to change this guy to a 6 pi over 3. So running out of room, so I don't have to rewrite it. I'm going to have to rewrite it. So that's going to be 10 pi over 3. So that's what I'm going to put right here, 10 pi over 3. Doo, 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 doo. All right, now we got to divide this whole thing by 4 to get rid of that 4 in the middle. So dividing by 4 means we actually multiply the denominator by 4. So we're going to get 4 pi over 12. Oh my gosh, these fractions are getting tiny. It's less than or equal to x, which is less than or equal to 10 pi over 12. Now, I know this reduces, both of these reduce, but they don't reduce to the same thing, so, but I'll reduce them anyway. We're going to have pi over 3, which is less than or equal to x, which is less than or equal to 5 pi over 6. So this is where our graph's going to start and end. Pi over 3 is where it starts, and it's going to end 5 pi over 12, not 12, 6. There we go. Good thing I kind of looked back at that. But anyway, so we're going to start here and we're going to end here. So this is kind of the area we're going to be working in. Now, kind of need to figure out the period. So let's go with 10 pi over 12 minus 4 pi over 12. And that is going to give us 6 pi over 12, which gives us pi over 6. No, pi over 2. Not pi over 12. Pi over 2. Now, this is where I grabbed those from. Since these already had common denominators, I used this as opposed to reconverting 3 pi over 6, or 3 pi over 3 and 5 pi over 6. I just used those because they already had common denominators. Worked out nice. So why do I want to know pi over 2? Well, I want to know my tick marks. So I need 4 of those tick marks. So this is going to be pi over 8. So every pi over 8 is going to be where my tick marks are going to be. So my tick marks are pi over 8. All right. Well, now what? Well, we can look at our amplitude here is half. So since it's cosine, I don't actually start on the x-axis. So I'm going to start on the upper line, the upper part of the amplitude. So that's why I got to write these here. So let's just put our first dot here. That's where we're going to begin our cycle, and this is where we're going to end our cycle. And 3 pi over 3 plus our first tick mark, which is pi over 8. Well, now we need to get common denominators here. And the only common denominators I see is 24. So 8 pi over 24 plus 3 pi over 24. And that's going to give us 11 pi over 24. Notice that's almost 12 pi over 24, so it's almost pi over 2. So I'm just going to put my first dot right here rather than divide up this line like a whole bunch because it's just going to be annoying. So I'm going to add another pi over 8 to get to my next tick mark point, but this turns into 3 pi over 24 again, which gives me 14 pi over 24. And that reduces to 7 pi over 12. Not that it really matters because I am not really going to draw those, but I know it's about somewhere right here. So on the test, you should probably just label these the points. That way you get your full credit. Anyway, we're going to add another 3 pi over 24, which will give us 17 pi over 24, which doesn't reduce. What a bummer. But I know that's going to be just a little bit past 2 pi over 3, so I'll just put that dot right here. And again, on the test, I would try and label this just so I get full credit. And then I'm going to add another 3 pi over 24, and that's going to give us 20 pi over 24, which should be 5 pi over 6. And sure enough, divide by 4, you will get 5 pi over 6. Yeah, 24 divided by 4 is 6. Yeah. Just double checking my math here. So that's at 5 pi over 6, and that's where we were supposed to end. So now we just need to draw our line here, and we're done. Now, I did do this the hard way because we were given this graph with pi over 6, pi over 3. So you had to kind of do some work to figure out where those points are. But we could do this easier if we were able to label our own points, which our instructor said we'll basically be drawing our own graph. So here's an easier way to think about this. I'm just going to write this part of it down really quick, and I need my tick mark. Since I've already done all the work for that part, I'm not going to redo that part of it. Pi over 8, yep. And then I'm just going to move this up over to the side here. I've already got a sort of blank graph. I did put the halves on there. But if you look at 3, 6, and 8, all the denominators, we come up with a common denominator for the three of those, and we're going to come up with 24. So 3, 6, and 8, common denominator, 24. Hopefully you can see that. So basically, I'm going to get 8 pi over 24 is less than or equal to x, which is less than, uh-oh, better do this quick, running out of battery. Less than or equal to 20 pi over 24. And that, of course, is going to mean our tick marks are a 3 pi over, oops, hang on a second, not over 8, over 24. There we go. Tick marks are 3 pi over 24. So how does this make this easier? Well, if you're going to label your own graph, you can do 8 pi over 24 because that's where we start. Add 3 pi over 24 for our next tick mark. So basically, I'm just going to add this. So that's 11 pi over 24. And then that's going to be 14 pi over 24. And of course, this means this will be 17 pi over 24. And then this last one is going to be 20 pi over 24, which is great. That means we did our math all correctly because we ended up with the same end point. Now, if you wanted to, you could go back and reduce the 8 pi over 24, the 20 pi over 24, and the 7 pi over 24. But for this, don't really need to. Since this is cosine and it's half, I'm going to put this at half, and then over the beginning, and crossings over the x and my lower point, and then I'm going to connect all the dots, and boom, there you go. That was just a quicker and easier dirty way to do it. So for 37, we're given this graph, and we need to determine the equation for this function. And, well, we don't even really have a full cycle here. We have like part of a cycle. So I'm just going to extend our graph out here. And it looks like we have about a quarter of a cycle. So I'm just going to bring it all the way out here. Let's see if I made it long enough. I'll label these tick marks. So 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 8 pi. Now I'm super visual, so that's why I like to draw things out. I don't know about the rest of you guys, but this is kind of where this cycle should be here, and then this one will be up here, and then this will be here. And I'm completing a cycle for sine starting at 0. So I'm starting, because I like to work with sine. It's easier for me to see. Sure, you could have done cosine from negative 2 pi to 6 pi, but then it does a whole bunch of wacky stuff with the x, and I like to keep it simple. So this is actually a negative sign because normal sine would go from 0 to positive 1, and then back down to negative 1, and then up to 2 pi. But you can see that this is flipped and stretched really, really long. So we'll get that out of there. Oops, I went too far. Ah, wrong color. All right, so I'm going to be working with negative sign here, and my amplitude is 1 because it's goes up 1 and goes down 1. So amplitude was easy to find, and my period. I'll actually write this here: y equals negative sign, and then I've got something to do with this x here, and I need to figure out what my period is so I can deal with that. Well, I can see my period, one cycle of sine is all the way out to pi over 8. So I'll just write pi over 8 here. Now, how it affects the x is affected, I showed you this trick before, but I just count the number of crossings of x after the initial, and I get 2, and then over the 8, which equals 1/4. So I'll just put 1/4 in here. Now remember the identity where we can move that negative sign on the inside. So we got y equals sine of negative 1/4 x. And that is the answer there. Now, of course, you could have done this as a period of cosine. You could do it as a period of negative cosine, or you could have done it as a period of positive sine. It just depends on where you decide to take that period, and then you just have to make the equation work for that period. So there you go. That's number 37. 38 is polar coordinate and identify and graph the polar equation. So I'm going to just put in some thetas and get some radiuses. So let's try theta of 0. So basically when I'm going to write all these other ones down here as well. All the ones I'm going to try. So 30, 60, 90, 140, well, 135, 180. Let's go with 225. That's another 45-degree reference angle. Let's go with 270. And since I did the 30-degree reference angle and 60-degree reference angle on the right side, I will do those as well for the negative portion of that. And we can do 360, which should technically be the same as what we get for 0, but we'll find out. So 0 at the angle 0, 2 minus 2 cosine 0. Well, when cosine is 0, what is it? Well, it's 1. So we have 2 minus 2 times 1. And 2 times 1 is 2, so 2 minus 2 is 0. So at 0, we get a radius of 0. We're going nowhere fast. So at a 30 degrees, we're going to have 2 minus 2 cosine 30. Cosine at 30 is square root of 3 over 2. So there we go, square root 3 over 2. Well, those 2's are going to cancel out. And so then we're going to, I'll just plug this into a calculator. It's easier for me because I'm going to ultimately need to subtract a radical and all that stuff. So anyway, what do we get? Point 0.27. Very small. So 2, whoops, minus 2 cosine 60 at a 60-degree angle. We can let's see, what's cosine at 60 degrees? Well, it's 1/2, right? So we have 2 minus 2 times 1/2 So this is going to end up being 2 minus 1, which is 1. So we'll just put 1 here. Now 90 degrees, cosine is 0. So the 2 times cosine is going to disappear. So we end up with 2 at 90 degrees. At 135 degrees, I was doing the every 30 degrees, but then I switched on this side to do every 45 degrees. But anyway, so cosine 135 didn't look very well, it just looked like a blob. Not that my penmanship's any better. But this is going to be, cosine is negative square root of 2 over 2. So we have 2 minus 2 times the negative square root of 2 over 2. These are going to cancel out, so are these. So we have 2 plus square root of 2, which calculator time for me. And it is going to be 2.7. There we go. I think. All right. Come on, Mr. Penn. Yep, there we go. All right. 2.7. That's what I get on that one. And then we have cosine of 180. So if we write that all down, here we go. Cosine of 180. And at 180 degrees, cosine is negative 1. So 2 minus 2 times negative 1, well, that's going to end up making this 2 plus 2, which is going to be 4. So for 180, we get 4. Actually, kind of running out of room here, so I guess I'll just erase all of these. We don't need all those anymore. We'll go and do the cosine of 225, which is a 45-degree reference angle from 180, or from 270, negative 45. So the cosine will turn into negative square root of 2 over 2. So 2 minus 2 times that, well, these are going to cancel out again, and then these are going to turn to positives. And so that is going to be 2.7 again. Now, 2 minus 2 cosine 270, cosine is 0 at that point. So 2 times, I'm sorry, 2 minus 2 times 0, well, that's going to be 2. And now we can start seeing this repeating pattern. So at 90 here. So I suspect that all of these reference angles are all going to repeat as well. I already know they do, so I don't actually have to go through and put them on the calculator. You can see this is a long drawn out task doing this way, but if you don't have them memorized, this is what you have to do. So we can start plotting these, and my little polar graph here is really kind of hard to see. So at 30 degrees, it's a dot barely away from 0. At 60, it's this dot right on the 1 ring. Oops. And at 90, it's a 2, so we'll be able to see this one. And at 135, it's 2 points. Whoa, it's 2.7. So almost to the third ring here. And then at 180, well, that one's all the way out to the fourth ring. And then we start reflecting everything that we have up above the x-axis, down below the x-axis. We didn't get any negative radiuses, so just going to continue around like this. So we get this little heart shape kind of pointing to the left here. Oops, of course, now it wants to make a circle. But 39, just going to do the same thing, make a theta radius chart. This time we'll do less. I'll just do the 45-degree reference angles. So 0, 45, 90, 180, 270, 315. Kind of skipped one there, didn't I? Or did I skip 225? 135? Yeah, 225 and 135. Yeah, I skipped some. I went 45. I just basically was starting to double stuff um, instead of adding 45 degrees to each one. Excuse me. Anyway, 4 minus 3 sine theta. Well, change our sine theta to 0 degrees. Well, at 0 degrees, sine is 0, so we end up with 3 for this one. Now, if we change our, this should have been a 4. So I end up with 4. Going too fast. All right. Anyway, we move on to 4 minus 3 sine 45 degrees. Well, at 45 degrees, sine is square root of 2 over 2. So we have 4 minus 3 times square root of 2 over 2. And we go to a calculator for this guy. We are going to end up with, I need to get better at typing in stuff on the calculator. I keep getting domain error. It means I plugged in something wrong for sure, because this should not produce a domain error. All right, so this turns out to be 1.88, rounding up, of course. So moving down the list here, we get to 90, and at 90 degrees sine is 1, so we are going to have this equal 1. So at 90 degrees, it's 1. Now 180, or actually, trying to see, trying to think where this is going to start reflecting. Well, let's do 4 minus 3 square root of 2 over 2. That was this guy. So for 135, it's going to be the same because sine is still positive square root of 2 over 2. So it's going to reflect the same on that side. So my bet is this is going to be this heart pointing down. So let's check this out at 180. Our answer is going to be 4, which is the same at 0. So let's do the next one. 270. The answer is going to be 7. Yep, sure enough, this is 4 wide at the x-axis, and it goes all the way down to 7 on the 270 degrees. So it's going to be a heart pointing down. And show the work for the negative signs. We're going to end up with 4 plus 3 square root of 2 over 2. Put that in the old calculator. Let's find out what those numbers are because it's going to be wider than the positive version of the square root of 2 over 2, or further spread apart, so that's going to be wider than what we saw at the other 45-degree angles. Write that down here. Let's see. Of course, when you're doing these calculations, make sure you're in your degree function. And this is going to be 6.12. So both the 315 and the 225 will be 6.12. And I checked it twice. It came out the same. So let's start plotting these guys. 0, 4. This is the 4 ring, or the number 4 ring. It's 2, 3, 5, 6, 7. I put a little 1 in the middle there, but you can barely see it. It just looks like a dot. Anyway, so at 45 degrees, we go out 1.88, so almost to the 2 on the 45 degrees, so that's going to be about right here. On 90, we are going to be at 1, so we are getting closer to the center. Barely see this dot. All right, so then, of course, at our 135, we would be back out here at 1.88. And then when we get to the 180, we are at 4 again. So you can see this is reflecting across the vertical axis, or the y-axis, from 90 to 270. At 270, we're out at the 7th ring, which is all the way to the edge of my circle here. Luckily, I had 7. And we kind of plot the rest of these points. This one's just over 6. Of course, that happens again over here at 315. And let's connect these. Well, sort of get the idea. Yeah, of course. All right, there you go. Okay, so number 40 kind of thrown us for a loop here. They're giving us tangent of theta and restricted between these two. That's normally where we think about tangent, but it repeats. Those are just the vertical asymptotes. So this is really negative 90 is less than theta, and theta is less than 90. So if we're looking at that restriction, that's where we're looking at our tangent function. So I'm basically going to just write out a little chart here so we can figure out what tangent thetas are and at what degrees. And this is kind of a good little chart to actually kind of memorize anyway. So if you're ever lost in the unit circle, you kind of know exactly where you should be. Because if you know this part of it, you can reflect everything left, right, up, down, whatever, and figure out where things are. So at 0, sine is 0, cosine is 1, so that means tangent is 0, because 0 divided by 1 is 0. At sine, we have, at 30 degrees, we have 1/2, and cosine is square root of 3 over 2. So we multiply that, or sorry, divide those, and we end up with square root of 3 over 3. And then, of course, at 45 degrees, sine is square root of 2 over 2, cosine is square root of 2 over 2, so that means tangent is 1. And the sine is square root of 3 over 2 at 60 degrees, and cosine is 1/2, so that means tangent is square root of 3. And then at 90 degrees, sine is 1, cosine is 0, so that means tangent is undefined. So we have we can't find that there. So, not this. What should I write next here? Let's do our theta, our Q, theta, yeah, let's make this look a little nicer. Come on, theta radius. There we go. So at 0 degrees, what is our radius? Well, at 0 degrees, tangent is 0, so radius is 0. 30 degrees, it's square root of 3 over 3. At 45, it's 1. At 60, square root of 3. 90, undefined. So let's see what we are at these guys. If we go to negative 30, we are negative square root of 3 over 3. 45 degrees, we are going to be negative 1. And so you can kind of see that basically if we go negative, we're just going to have negative the same thing on the other side. So it's kind of mirrored. Now, normally on a Cartesian plane, this would be just this little weird S-looking thing going from quadrant 3 into quadrant 1. However, when we go to the plane that we're looking at now, because we're going to go up by degrees, at 0 degrees, we're at 0. At 30 degrees, square root of 3 over 3. So we're going to be somewhere right. Doing the calculator here. Doesn't really matter. You're not going to see it. It's going to be somewhere right in here. At 45 degrees, we're at 1, which is there. And 60 degrees, we're at square root of 3. So we'll be a little bit further out here. So you can see this is just kind of making this use section, which is what we would normally see on our Cartesian plane for this portion of tangent. However, since we're restricted between negative pi over 2 and pi over 2, when we look at the negative portions, we also get a negative radius. So that means at 30 degrees, we'll be in what we would kind of look at as the quadrant 2 here, but it's not really. So we end up with this parabola looking thing. So that's what this graph ends up looking like. All right, so on to number 41. Write the expression in standard form a plus bi. So we have to recall our theorem here. So z to the n is equal to r to the n, and CIS, which is cosine n times theta plus I sine, forgot the I sine n times theta. And there you go. That's one thing we have to remember. Get this thing done. The next thing we have to remember is r is equal to the square root of a squared plus b squared. And let's see, a plus bi, that's what we want to get to. So we already have our, we need to find what our radius is. And we have our a and b, they come from this. So that's our a and that's our b. We have 1, and that we don't write 1i normally, but there's a 1 in front of that I. So a is equal to 1 and b is equal to 1. So we can find radius by using this formula. So r is equal to 1 squared plus 1 squared. Now, 1 squared plus 1 squared is 2, so the radius is equal to the square root of 2. There you go. Now we have one part of this equation. Now our n is this 20 here, so n is equal to 20. Yeah. So now we have a little bit more, so we can plug things into this formula here. Since we know what the r and the n are, the r is, oops, square root of 2, and that is going to be to the power of 20. And kiss is going to be 20 times theta. Now we need to figure out theta is. So find theta. Well, to find theta for these problems, we use tangent theta is equal to b over a. Well, we know what our b and our a is. It's 1 over 1, which is going to equal 1. Now, where is tangent equal to 1? Remember that chart I used earlier? That would be a really good thing to have written down in your notes or as soon as you sit down to take the test, because it would help you find this. But square root of 2 over 2 over square root of 2 over 2, or a 45-degree angle, that is where tangent would be equal to 1. So we can put all this in. So we have square root of 2 to the power of 20. Kiss 20, and our theta is pi over 4. There you go. Now we can reduce a bunch of this stuff here. So we can get rid of the 20 and make that 5 and get rid of that. So we end up with 5 pi. So cosine of 5 pi is basically the same as pi. So cosine is negative 1 at 5 pi. And sine at 5 pi, or even at pi, is 0. So we can rewrite this whole thing as square root of 2 to the 20th and minus 1, because that's the cosine part of it, plus I 0, because that's the sine part of it, or 0i. And then we can get rid of this because that's going to equal 0. And negative square root of 2 times to the 20th power, put that into a calculator, and we're going to get negative 1024. So there you go. So 42, we're basically going to do exactly the same process. We're going to find our A, which is 1, and our B, which is negative 1, actually. There we go. And we need to find our radius. And our radius is found by the square root of 1 plus the square root of negative 1. Or not the square root. The square root of 1 squared plus negative 1 squared, which is going to end up being the same as the last problem, which is r is equal to square root of 2. Then we need to find our theta, and our theta comes from tangent b over a, and our b is negative 1, and our a is 1, so this is negative 1. Now if we think about where tangent is negative 1, it's either in quadrant 2 or quadrant 4. So, and we're going to be talking about one cycle of tangent, so it'll be, let's look at quadrant 4. That's where it would be negative. So will be tangent of negative pi over 4. Now remember our r to the n times kiss, and then n times theta 10 times theta. Oop, kind of getting ahead of myself here, actually. Should have just erase n r to the nth, or actually, let me just remove this whole thing and write down the whole equation that we're subbing into, r to the nth kiss n times theta. Excuse me. So now I'll sub in. So we have square root of 2 to the 10th times kiss 10 times negative pi over 4. Now inside here we can reduce the 10 and the 4, because this is going to end up being negative 10 pi over 4, so we might as well make this 5 pi, negative 5 pi over 2. So that's what that guy's going to end up being. Write the CIS in front of it, that guy, finish out on my brackets, and then we got the square root of 2. This will end up being a 5 as well, and that will get rid of our squares, square root anyway. So we have 2 to the 5th, and at negative 5 pi over 2, which is really the same as negative pi over 2. It's just gone around a couple more times, rotating around. So cosine negative 5 pi over 2 is equal to 0, because it's gone around. And sine is of negative 5 pi over 2 is going to be negative 1. So we sub these in. So cosine is our A, which was 0, and plus I negative 1. And then we have 2 to the 5th is 32. So 32 times 0 is 0. So we are going to end up with 32 times negative 1, which will just make this negative. So negative 32i. And that is the end of 42. All right, so for 43, we end up with something ugly, but see if we can work through it. We're going to look for our A, B, our radius, our theta. So our A comes from here, so it's negative square root of 3. Our B comes from here, it's 1. Now we can find our radius by r is equal to the square root of a squared plus b squared. And our a is negative square root of 3, so square root of 3 squared. And this, of course, is negative in here, but it doesn't really matter because negative times negative is going to be positive. Plus 1 squared. Let's make this so you can actually see, so it's starting to look like scribble. There we go. Now you know that that is a negative square root of 3 and it's squared. There we go. And so squaring a square root of 3, that's just going to end up being 3. So 3 plus 1 is 4. So we are going to get square root of 4. And the square root of 4 is 2. So it was almost too easy. I had to think about it for a second. So radius is 2. Now we're going to find our theta. We have 1 over negative square root of 3, which if we fix these radicals, clear it out of the denominator, rationalize rather, we get square root of 3 over 3, and that's negative, of course. Now, when is tangent negative square root of 3 over 3? Well, it's at negative pi over 6. And remember that chart I had earlier, we saw square root of 3 over 3 was at pi over 6, but since this is negative, it's negative pi over 6. Oh, yeah, we got to find our n as well, which is 6, raised to the 6th power. So here's our r to the nth, kiss, n times theta. So we can plug all of our information that we have in. Our radius, r to the 6th, or 2 to the 6th, kiss, 6 times our theta, which is negative pi over 6. That is not 6 minus, but anyway, these 6's are going to cancel out. So we're going to end up with negative pi. So the 2 to the 6th, kiss, pi, negative pi over 6. Nope. We canceled out that 6. There we go. Minus pi. There we go. So let's see here. Don't know this in my head, so I had to use a calculator, but 62 cosine negative pi plus I sine negative pi. So cosine at negative pi is negative 1, and sine is 0, so we have 0i, and 2 radical 6. It shouldn't be 62. Let me do this again on my calculator. 64. There we go. That looks better. 64, so I mean 64 here. So 64 times negative 1 would be negative 64. And that's the final answer there. And our last one, number 44, is identify and graph the polar equation. Now, if you recall, r is equal to a sine 2 theta. This is going to produce a 4 rose petal at distance of a. So our a in this case is 4. So we're going to have these loops, 4 of them, one in each quadrant, that goes out to distance of 4. And as I remember, since it's 4, they're going to be uniform away from each other. So they're going to be on the 45-degree axes. I don't know. That's 40-degree radials, actually, I think. So here's the 4, the 4th ring. 1, 2, 3, 4, yep. And here are our peaks for our 4 petals. And they're, of course, going to join at the middle. So I can just draw these loops in each of these quadrants. This one kind of dipped into the negative, so let's redo that one. It's got to stay above the 0 line to the right of 90 degrees for this one. And this has to stay to the right of 270 and below the 0. There we go. That one didn't look very good. None of them actually look the same as the other, so I guess it doesn't really matter. But there you go, number 44. Well, hang on. What's this number 19? And it's not like number 19 that's on our review. Well, speaking with our instructor, there's a couple problems that he didn't put on our review that will come up on our final. So I pulled this problem from our review for our 4th exam. So exam 4 has number 19. It looks like this. So I brought it over here, and it'll just be kind of a reminder of how to do this type of problem. So when you see it on the final, you'll know how to do it. So for number 19, we're going to try and get rid of y. So it's simpler because there's only two values. We'll multiply this top one by times 2, and we'll bring the bottom one straight over. 3x squared minus 2y squared equals negative 6. Multiplying this top one times 2, we will get 4x squared plus 2y squared equals 34. Yeah, 34. So now we're just going to add these two guys together. We're going to get 7x squared. This cancels out. And then this is going to be 28. So 7x squared equals 28. Solve for x. X squared equals 4. And then the square root of that is plus or minus 2. So we will try and figure out for x equals 2 first. We're going to look at, I'm just going to use this formula. I'm going to plug in 3, and I'll plug in my 2, positive 2, minus 2y squared equals 6. Now I'll solve for y, and I'm going to get, this is going to be 12 minus 2y squared equals negative 6. Subtract 12 from each side. I'm going to get negative 2y equals negative 18. Then I'm going to divide by negative 2. So y is going to, these are squared, y squared is equal to 9. And that's going to mean my y is equal to plus or minus 3. So basically, I take my 2, which was my x value, and I'm going to get two ordered pairs here. I'm going to get 2 plus 3, and I'll get 2 minus 3. And of course, we don't say plus 3, we just say 3. So fix that guy. There we go. Now, if I use negative 2, so x is equal to negative 2. Remember, I had a plus or minus over here, so I need to find some more ordered pairs. So 3 times negative 2 squared minus 2y squared equals negative 6. Just using the same formula. This is going to be 12 minus 2y squared equals negative 6. This is the exact same place we were at over here. They're the same. So I know that I'm going to get y equals plus or minus 3 again. So my next two ordered pairs are going to be negative 2 comma 3 and negative 2 comma negative 3. And there you go. That's number 19. Now there's two other additional types of problems that are added to our review that weren't on our review. So I'm going to do a couple examples of each of those types, and then should be getting close to being done. So on this one, we can factor out a cosecant. So we end up with cosecant theta times the quantity cosecant to the fourth theta minus 4. And then that gives us a difference of squares. So we have cosecant squared theta plus 2 times cosecant squared theta minus 2. And of course, in the beginning here, this all equals 0. This is cosecant theta. So what makes this 0? Well, cosecant theta equals 0. Well, that's the same as saying sine is 1 over 0. Battery. Well, this is undefined because you cannot divide by 0. So this can't happen. So this is not a 0. So let's move on to the next portion. We have cosecant squared theta plus 2. We'll set that to equal 0. and that is cosecant squared theta equals -2. Now, you should be able to tell at this point that this is not going to work out, and here's why. Cosecant theta, you're going to square root both these sides. You're going to get a plus or minus square root of -2. This is an imaginary number when you have a negative inside the square root, and so that is not a real zero. So let's do this last one. Cosecant squared theta minus 2 equals 0. Well, that'll be cosecant squared theta equals 2. And then we'll square root that, and we'll end up with cosecant theta is equal to square root of 2, which is the same as saying 1 over square root of 2, which would rationalize. Well, let me actually write this for you. Sine would be equal to 1 over square root of 2. Well, then we are going to rationalize this by multiplying by square root of 2, and then we'll have square root of 2 over 2, and this is actually going to be plus or minus. I forgot to put that in here, plus or minus. So we have to carry that across to all the rest of this. So sine theta is equal to plus or minus the square root of 2 over 2. Well, where's sine square root of 2 over 2 or negative square root of 2 over 2? Well, it's going to be all the pi over 4s. So I'm just going to put pi over 4 a whole bunch of times here. Not a whole bunch, 4 times, because it's just one cycle. So it happens at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. So that is that one. Here's another one, the similar idea here. We're going to find out where it happens on just one cycle. I missed that in the directions there, but that's what you're supposed to do. So this transitions to 4 sine squared theta equals 3, and then you bring the 4 over, and then basically you end up with sine theta plus or minus the square root of 3/4. Well, that reduces to sine theta equals plus or minus the square root of 3 over 2. Well, where is sine square root of 3 over 2? Well, again, we're going to have 4 answers because there's 4 places on the unit circle where it's either plus or there's 2 pluses and 2 minuses. And it's a 60-degree reference angle, so it's pi over 3. So I'll write my 4 pi over 3s, and I start at 1, and then it'll go to 2. And then 3 pi over 3 isn't 1 because that would be at the 180. So I go to 4 and then 5. And those are the numbers for this guy. Now these next couple, I already did show you an end behavior earlier, but I'll show you a couple more end behaviors here because this actually has some other things going on in it. So the first things you want to do is find the zeros. Well, what makes this function 0? Well, my zeros are going to be, well, 0, because 0 times -3 would make this 0. And the other one is -2. So -2 plus 2 would be 0. Squared would be 0. So I'm just going to plot these two zeros. So we've got 0 and -2. Now, if we look at this function, we can see it starts with this negative sign. Well, that means this function's going to end negatively or in the negative quadrant. So it's going to end over here in quadrant 4 because it's negative. Now, the first x is a coefficient or exponent of 1, and that's odd. Not odd as in, that's weird, but it's an odd number. And the 2 is an even. Well, evens bounce off of the x-axis and odds go through. So if I'm going to start somewhere here in quadrant 4, I'm going to go through this 0, and I'm going to bounce on this one and go up. So that's how you know whether it crosses or bounces, because of the odd or the even exponent of where that 0 comes from. And then we'll do one more of these. So we'll find these zeros. And these zeros are, again, 0. Let's see, 1 and -2. So I'm going to plot those 3 points here because that's where something's going to happen on the x based on the exponent. Since it's positive, it's going to end up here, and these are odds, so we're going to pass through every single one of these. So our sketch would basically look like this, moving backwards to the beginning. All right, guys. Well, that's it for this review. Good luck on your final. Good luck on all your finals. And I hope to see you in Math 3A or Calc 1 next semester. Otherwise, peace.